Alright, we're down to our last problem. This is number 14 from the Gauss Law WebAssign. This comes from chapter 24 in Serway and Jewett, edition number 9. This is problem number 36. So this is a quite involved problem. Unfortunately, there are no intermediate little checks that we can make sure that we're doing it right, so we have to be careful all the way through. So the idea here is we have a big charge Q. On the inside, I'm going to call it Qn. That's just Q inside of a spherical shell of radius R1 and radius R2. Now Q on the inside is negative, and the spherical shell, we're told, also has a charge density that is negative. Okay, so everything here is negative. The idea is there's a proton, and what are the words? A proton moves in a circular orbit just outside the spherical shell. So those words mean that essentially the radius that the proton is going to be traveling is the same as R2. Alright, so I'm going to draw it out here, and I'm going to call it positive little e, that's the charge, and then this little guy has a little mass of the proton, and this is going to move in the circular path. And the question is, what is the speed of the electron? Okay, so why does the proton go in a circular path? The proton goes in a circular path because there is a force. The electric force is trying to pull it inward, right? And because the proton has speed, it's going to travel in a circular path due to centripetal forces. Okay, so that's the idea. So let's write some of our knowns. The Q on the inside, for me, it is actually for everybody, it is minus 60 nanocoulombs. Finally, we got something inside the micro, so it's 10 to the minus 9. Okay, R1, we are told, for everyone is 20 centimeters, and then R2 for me is 29 centimeters, 0.29 meters. The density, we are told, is negative, and everybody has a different number, times 10 to the minus 6 coulombs per cubic meter. Okay, and yeah, so it's going to be important that we eventually calculate what the charge enclosed in this path is. The orange line is the path of the proton, and it's also going to be the shell of our Gaussian surface. So we're going to need to calculate what the charge enclosed is going to be. We know this charge inside here, Qn, is given, but what is this Q shell? Okay, so let's calculate that. We know, let's see here. Yeah, I'll do it over here. We know that rho is the charge density. Okay, and so Q, whatever Q we're looking for, is rho times whatever volume we're dealing with. And what we're looking for is the Q of the shell here. What is the charge Q of the shell? Well, that's going to be rho times the volume of the shell. And the volume of the shell is the volume of the outer sphere, V2, minus the volume of the inner sphere, V1. Okay, and so these are spheres, so we have a rho. This is 4/3 pi big R 2 cubed minus the volume of the inner. Okay, so we can pull out a 4/3 and a pi, and we get R2 cubed minus R1 cubed. Okay, so let's go ahead and plug those numbers in now, and let's get a value. I don't often like doing this. I like to play with variables most often, but I think this is going to be best for this situation. So rho is negative 2.62 to the minus 6 times 4 times pi divided by 3. And we're going to multiply that by R2, which is 0.29. And we're going to cube it. And again, let's go to math, 3 to cube. And we're going to minus 0.2 cubed. Okay, and for that we get the charge of the shell is negative 1.799 times 10 to the minus 7 coulombs. Alright, that's just the charge of the shell. And again, we're going to need the total charge enclosed by the Gaussian. And so that Q enclosed is going to be the Q on the inside plus the Q of the shell. Okay, so we can figure that out. Q on the inside is this guy, negative 60 e to the minus 9, plus the Q of the shell, which is what we just calculated. So I'm going to use my answer, second answer. Negative 2.399 10 to the minus 7 coulombs. Alright, so what are we going to do with that? If we look at the physics of why the proton is actually orbiting, it's a centripetal force problem. So the sum of the forces acting on that proton is equal to ma, and because it's centripetal acceleration, it's mac. And there's only one force acting on that proton. So that force pulling it in toward the center is the electric force, and it's due to the interaction of the proton with all these negative charge distributions to the left of it. So so there's only one force. So this is Fe, mac, and because we are interested in the speed of the proton, we are going to look at this equation, mv squared over r, where m is the mass of the object orbiting, so it's the little mass of the proton, and r is the orbital radius, which is just above it, so it's going to be, ends up being r2. We're looking for v. That's our holy grail here for this problem. What is the electric force acting on the charge? Well, we know that a charge embedded inside of an electric field has a force that's equal to Q, the charge that's embedded in the field, times the electric field. Okay. The electric field, we know, is going inward because these are, the charges on the inside are negative. So if this is our Gaussian surface, the electric field is coming in, and the differential area is pointing outward. Okay, so we need to figure out what this electric field is going to be so we can plug it in. So that brings us to, there's so many different little areas here. That brings us to Gauss's law. Okay, and because E and dA are anti-parallel, this is going to be a negative EA. All right, and we should be clear here. This is the electric field on the outside of both charges. Okay, so I'm going to call it E out. Let's see. So E out. Just in case we ever wanted to use this equation again for some other problem, we would remind ourselves that it's only useful for the outside of the charges. Over, I skipped a step here. The area, as we know, the area of our sphere is 4 pi r squared. So 4 pi r squared, and then don't forget the epsilon naught. Okay, but this is minus q enclosed. 4 pi epsilon naught is k. Coulomb constant, and then 1 over r squared. Okay, and for this problem, Q enclosed, we just calculated that. And for this problem, the electric field, where do we want to figure out the electric field? We want to figure it out right where the electron, the proton, gee whiz, is traveling, and that is R2. Right above R2, so we're just going to assume it's R2. So R2 squared. Alright, and so when you do that calculation, so we're going to take K, which I have built in, and it's a minus K, I should put minus K, times the previous answer, divided by R2 squared. And we get 2.567 times 10 to the 4th newtons per coulomb. So that is our electric field. So we're almost done. So we're trying to find the velocity. And so this equation here, V is equal to the square root of Q E R over M. And again, for this problem, the charge is the charge that's embedded in the electric field, which is the charge of the proton. I'm going to call it little e. E is the electric field, which we just found here. R is the radius of the orbit, which is R2 for this problem. And M is the mass of the proton. So forgive me for not writing it in. You might need to refer to your equation sheet for some of these numbers. So we'll start off with the square root. E is the charge of the proton. Okay, times the electric field, which is the number we just calculated. So I'm going to use the answer. Times R2, which is 0.29. And then we divide by the mass of the proton, right? It's a proton, so 1.67. E to the minus 27. All right, let's see if that gives us the right answer. 8.445 times 10 to the 5th meters per second. Let's see. Um, 8.45 e to the 5th. Fingers crossed. All right, we're done.